Welcome to the Week 4 overview. This week we'll be discussing the economics of the bioprocess. Bioeconomy refers to any activity that makes use of bioinnovations based on biologic sources, materials, and processes to generate sustainable economic, social, and environmental development. The justification for commercialization of any scientific finding is its potential to provide a marketable product and to generate a return on invested capital. Basic discoveries in life sciences over the past 10 years have already created a family of novel biopharmaceutical products with novel therapeutic and prophylactic potential. Worldwide, annual sales have grown from zero in 1980 to $4 billion in 1991 to $50 billion in 2000 to over $300 billion so far in 2016. There are multiple factors that need to be considered before pursuing a project biomanufacturing. Preliminary economic evaluation of a project involves estimations of capital investment and operating cost, as well as an analysis of profitability. For biopharmaceuticals, there is an additional factor, the cost of new drug development. This includes the research and development spending for all products, both successful and unsuccessful. The actual average development cost per successful drug is only between $20 and $50 million. However, since more than 90% of these projects are never commercialized, the average R&D cost skyrockets to the range of $200 to $500 million. This reinforces the need for an effective process design, tools, and methodologies to efficiently evaluate and eliminate non-promising, non-profitable projects at an early stage of product and process development. For an economic assessment, the first step is an estimation of capital investment, and this is usually based on the cost of the brick-and-mortar facility as well as any necessary equipment. Operating costs of the process can be derived from the cost of items such as raw materials, personnel, energy, etc. Ultimately, a profitability analysis will be conducted to examine the expected revenues and sets them in proportion to the cost and a number of other factors such as time, value, money. This figure shows a very simple description of factors which are associated with either capital investments, which are shown on the right, versus operating costs, which are shown on the left. Things such as capital equipment include purchase costs, whereas operating costs include raw materials. This figure was taken from the Nature Biotechnology article in our assigned reading for this week. And it simply shows a breakdown of the categories for the U.S. biotech revenues in 2012. It shows basically that there are three primary categories: biologics, industrial, and genetically engineered crops. Under the industrial component, there are things such as biochemicals, biologic feedstocks, biofuels, and other new materials. This slide shows a slightly different breakdown. It shows the increase in revenues generated by U.S. technology companies, and this focuses on public companies in the U.S. between 2013 and 2014. As you can see, the revenues increased for these public companies from $99 billion to $123 billion in 1 year. That's a 24% increase. In contrast, their R&D expenses only increased 20%. But overall, in terms of sales, what we see is an increase from $4.5 billion in net income to $14.9 billion in net income increase. That's 231% increase in net income. While the readings and other assignments this week give you a lot of details in terms of decisions and how they are based on the economics of the product, I thought it would be helpful to provide 3 specific examples in different areas on how the economics or profitability have influenced bioproduct development. And the 3 examples will include a pharmaceutical drug, a bio. The first example I want to talk about is Taxol. It's a chemotherapeutic agent which is currently used for a number of cancers. It was initially identified in 1967 from the bark of the Pacific yew tree. Years ago, it was used by American Indians for the treatment of inflammation. And more recently, it was developed as an anti-cancer agent. The mechanism of action of Taxol has been defined as the inhibition of cell division by stabilization of microtubules. In the 80s, it underwent 2 successful clinical trials where it showed a remarkable response rate in 30% of patients with refractory ovarian cancer. But the problem is a limited supply. To prepare 10 grams of pure Taxol requires it to be isolated from 1,200 kilograms of bark. This would result in the annual destruction of over 360 yew trees. Since Taxol is highly effective for treating cancers such as ovarian, breast, melanoma, and lung cancers, the problem was, how do you produce enough of it without killing so many yew trees? The solution was Taxol is now produced using plant cell culture technology developed by Phyton Biotechnology. It uses a Taxus cell line in large fermentation tanks. And as a result, this company has annual sales of between $2 to $3 billion. The second issue we want to talk about today is biofuels. We're all affected by the amount of oil and the price of oil every day on our way to work. On this example of Canadian oil production, about 1/3 of all oil currently produced in Canada comes from oil sands. Oil sands are composed of sand, silt, clay, water, and about 10% bitumen. Oil sands are either surface mined or the bitumen is extracted in situ. Using today's technology, about 174 billion barrels can be recovered. It is predicted that ultimately about 315 billion barrels will ultimately be recovered. So what is the economics of this? To produce 1 barrel of oil from oil sand, 4 tons of raw material must be mined. 2 to 5 barrels of water are used to extract the bitumen, and then natural gas is used to heat the water to create steam for extraction. There's enough natural gas used to heat this for 1.5 homes. When gas is selling at $4 a gallon, this is economically feasible. But when gas prices drop to $2 a gallon, suddenly this process is no longer efficient. The decreasing worldwide oil reserves and the high cost of generating some of the oil from oil sands has led to search for other alternatives. One of those is biofuels. So what is a biofuel? A biofuel is any solid, liquid, or gaseous fuel derived from biomass. That is a recently living organism or their metabolic byproducts, such as manure from cows. And that is in contrast to fossil fuels, which are derived from long-dead biologic materials. How are biofuels produced? Initially, biofuels were derived from sun-captured materials through photosynthesis by the plant, used as feedstock for biofuel production, and stored in the plant cells. Various plants and plant-derived materials have been used for biofuel manufacturing, such as sugar crops, natural oils from plants like palm oil, soybean, or algae. wood and its bioproducts, flaxseed, and waste from industry, agriculture, forestry, as well as households. So one of the issues with biofuels, or in this case we're talking about biodiesel, is it uses triglycerides. Triglycerides derived from current oilseed crops and waste oils cannot meet the U.S. diesel demand, which currently is about 60 billion gallons per year. The entire U.S. soybean crop can only produce approximately 2.5 billion gallons per year. It's estimated that worldwide production of biodiesel would only yield 13 billion gallons per year. And realistically, the agricultural productivity cannot possibly be diverted from a food supply to the production of biofuels. So, while this approach represents an attractive biostock for biopetrochemicals, it would mean that there would be less available for potential use as foods. So how do we circumvent this issue? Well, microalgal cultivation is an option. Inexpensive culture systems using shallow ponds stirred with paddle wheels in areas with high levels of sunlight. More intensive cultivation systems are now becoming available. Using this approach, algal cultivation can be 50 times more productive than traditional crops. And this has potential for culture in areas not used for crop production, such as the ocean or various desert lands. This slide provides some examples comparing potential oil yields. If one looks at corn, corn can produce about 18 gallons of oil per acre. Soybean, about 48 gallons per acre. In contrast, algal cultures can yield up to 10,000 gallons per acre. As you can see from this chart, the revenues being generated by this biotechnology approach to biofuel generation has been steadily increasing since 2000. And at this point, we're now reaching about $40 billion in revenues from biofuel production. The third example, in this case, is the development of ZMapp and how it's produced by biomanufacturing. To treat Ebola virus infection, monoclonal antibody therapy was developed. The initial treatment was termed ZMapp, or Z monoclonal antibody, which was developed as a mixture of 3 mouse monoclonal antibodies recognizing Ebola virus surface glycoproteins. These 3 monoclonal antibodies were then chimerized with human constant regions in order to prevent autoimmune responses against the antigens. Sort of briefly described, initially mice are infected with the Ebola virus. They form antibodies. You remove the spleen from these animals and create hybridomas. And these hybridomas that produce a monoclonal antibody are then genetically engineered in order to be so that the antibodies contain the human constant region. That way, they are not attacked by the human immune system when they're used for treatment. This gene is then removed from the hybridoma, and then it is infected into a tobacco plant, and then this genetically modified leaves then make large quantities of the antibody. As we've previously discussed with other genetic modified organisms in order to create a more effective treatment or production system, plant-based drug production is faster and cheaper than traditional methods. In this case, you can go from immunization to clinical grade products within 4 to 6 months. Just giving you an example, initially you isolate antibodies that attach to the Ebola virus that prompted the immune attack. You grow tobacco plants hydroponically, and you genetically re-engineer the tobacco virus to carry the antibody genes into the plants. The infected plants become factories for the plant virus and the antibody cargo which overtake their host. Ultimately, within 7 to 10 days, the plants die. The dying plants are then harvested. The cloned antibodies are then separated from the plant material, purified, and formulated into doses, and then tested to ensure quality. Returning to the economy of biotechnology, the approach is to manage strategy according to industry sectors and incorporating a value chain approach. Currently, there are 3 thematic sectors. There's agriculture, health, industry, and environment. The applications to agriculture ensures food security, enhances nutrition, improves health, enables job creation through expansion and intensification of sustainable agricultural products. Some of the strategic projects which are ongoing are crop and livestock improvements, both for biotic and physical stresses associated with climate change, including indigenous crops, agro-processing initiatives, and integrated food nutrition research programs, animal vaccines capability, energy crop initiatives, biocontrols and biofertilizers, agriculture, soil conservation, and water resource management. Within the health sector, the bioeconomy supports and strengthens the capability to manufacture vaccines, biopharmaceuticals, diagnostics, and medical devices to address the diseases while ensuring security of supply of essential therapeutics and prophylactics. Ongoing strategic projects are development, improved therapeutics and drug delivery systems to address diseases, develop new and improved vaccines and biologics, develop improved diagnostics, develop improved medical devices, clinical research and development capabilities, and establish and expand pharmaceutical manufacturing. Industrial and environmental applications to the bioeconomy include support research, development, and innovation in biological processes for the production of goods and services while enhancing water and waste management practices to support a green economy. Ongoing strategic projects include strategic industrial biotechnology programs, strengthen and develop bioprocessing capabilities and capacity, develop integrated biorefineries from bio-based feedstocks, strengthen wastewater research, development, and innovation, strengthen waste research, development, and innovation, and synergies with enabling and emerging technologies. So in summary, the benefits of the bioeconomy strategy are that science-based biosolutions can be used to manufacture high-value protein products such as biopharmaceuticals and vaccines, produce biofuels, improve and adapt crops, remedy industrial and municipal waste, reduce production cost, reduce environmental impacts, improve the global competitiveness of the health, agricultural, and industrial sectors for the quality of products. It can allow us to respond to global challenges such as the burden of diseases, ensure food security, enhance our competitive industries. It can allow us to adapt to climate change and changing energy requirements.